Yeah. Okay, so we're going to say a few more things about capacitors. We had one capacitor topic we didn't get to, so we want to get to it. I want to... Audience left. Okay, there we go. Yeah. Okay, one capacitor. Let's do a quick one-board review of everything you learned about capacitors. So if capacitors were entirely confusing, now that you've thought about it for a couple days, maybe this will help. So the capacitor really is a device. Okay, it's really two parallel plates. It's a device that illustrates everything that we've talked about in electrostatics. Okay, one question already, probably about the exam. It does not cover Gauss's law. On Canvas it says the homework problems are due Saturday. Can they be, please? Are they, can they be, question mark, please? So you have to make an actual request. They're due Saturday. Maybe you're asking to make them Sunday. They were supposed to be due today, but I was so far behind, I moved them. Sunday might be reasonable, but I need a complete sentence with a verb and a subject and an object. Okay, capacitor is two conducting plates with opposite charge because you connect them to a battery. Remember, the battery gives you some EMF volts. It has a positive terminal and a negative terminal. And you take a conducting wire and touch the conducting electrode and touch it to the conducting plate. And we know that a conductor, in electrostatics, everything goes to the same potential. So if this is at the high voltage, the high potential, this is at the high potential, the wire's at the high potential, and therefore the electrode's at the high potential. To get to the high potential, charge has to flow there. Okay, if this is going to be at a high potential, we need positive Q to flow out of the battery and onto the plate. Okay, this must be the day request. Is a pledge problem due next Tuesday? Yes? What? Yes. Yeah, there is a pledge problem out right now. I believe Tuesday was the date. For the negative one, you also have a wire, bringing that electrode to a negative potential. The same potential as this electrode, this wire, this plate. Electrostatics say all that metal has to be at the same potential. So some negative charge has to flow out of the battery. Okay? So you take these plates, hook them to a battery, charge flows, and then the two electrodes, or I'm sorry, the two plates are at the same potential as the electrodes. They have properties like an area, and they end up with a certain amount of charge, minus Q and plus Q. They have the same magnitude of charge. One's positive, one's negative. Therefore, you could calculate, if you felt like it, the charge density on the plates. That's sometimes useful. I'll show you why in a minute. So we could calculate this one as just plus Q over A. That's just the little sigma that we call the charge density. You could define the distance between the plates as useful, right? That's about it, okay? So the battery sets the potential difference. 2, usually the battery's property is called the EMF, the special curly E of my 4 E's, the special curly one. Okay? And the reason it's called a capacitor is when you apply a potential to it, the capacitor holds a charge. It has a capacity to hold on to charge. Apply a potential, you get a certain capacity to hold a charge Q, and this is just the definition of the capacitance. From physics, we did derive that there's a linear relationship between how much voltage you apply and how much charge you get, and the capacitance is just the constant of proportionality between those two. Okay? This is just for parallel plates. That's the capacitance. All right? And we talked about how you can calculate it, but it does depend on geometry. So C depends on the geometry. And to calculate it, you do it different for every possible geometry. So you don't really have to have two parallel plates to be a capacitor. Any two conductors technically are a capacitor. I'm a conductor, you're a conductor, technically we are a capacitor. If you took a battery and you held onto one wire, I held onto another wire, charge would flow, we'd have opposite charge, we'd be at the same potential but opposite, and we would be a capacitor together. That'd be kind of cute. It'd be like a Valentine's card. Two people holding on to, oh, it's too late. Sorry, Valentine's Day's over. We're all jaded. Sorry. Okay, so capacitance depends on geometry. So for the capacitance, sometimes you'll see it like this. For a parallel plate, that just means parallel plates, little drawing. Epsilon naught, my second funny E, A over D. Area over distance. Or, yeah, the separation. Okay? So we derived that last time. It's just you think about how does the field depend on the potential and how does the charge depend on the field, and you move it around. But the key idea is two parallel plates have a capacitance. It doesn't matter what charge is on them. It doesn't matter what the battery is doing. It doesn't matter what delta V is. It's an inherent property of two conductors and their geometry. So you and I, we could calculate the capacitance between us. It would be very low because we're very far apart. Let's keep it that way. Okay. Now, one big question is the field. You know, a classic capacitor question is, what is the field inside the gap here? That's my third E with the arrow on it. Field inside the gap for a capacitor, you can get two ways. I haven't really stressed it probably enough, but one way is from the potential and the separation. Okay, the field between two plates, if they're big compared to their separation, they're essentially infinite, is just this delta V over the D. So if you're given the voltage and the distance, the separation, you have the field. But another way you remember to get the field is if you have the charge density. So it's also equal to the charge density on the plates over epsilon naught. It's equal to both of those. So in a problem, you might be given this one, and that's how you get the field. Or in a problem, you might be given, they didn't tell you the voltage of the battery, but they told you how much charge is on the plates. Oh, divide the charge by the area. You have sigma. Oh, now you have E. Okay. Then you don't even need the separation. Okay. This brings up a weird thing. Somebody did ask last time, how can E be constant anywhere you go when you're closer to one plate than the other plate? Okay, you have to read all the chapters to understand that, or take 102. But believe me, the E field is uniform. Even if you almost touch the plate, the E field is still constant. But you're going to touch a charge. How can that be? Oh, you got to read all those chapters and take 102. Sorry. Well, I'm not going to tell you. I've got to have some suspense in your life. So let's see, there were this equation is important. And then we calculated that it's not really storing charge that we care about. It's that it stores energy. Usually in a circuit, this is what you want. And this is the one I did at the very end last time. And there was no mistakes. I just calculated the wrong thing. That was the main answer we got. Q squared over 2C. Shouldn't the field lines point towards the negative plate? Oh, I wasn't really being precise here. Well, first of all, those aren't field lines. Those are E field vectors. But you're right, I drew them the wrong way. Thank you. So you may remember this calculation of the energy was complicated because we had to think about when you move the first charge from one plate to the other, there wasn't a potential yet. But it built up a potential. And then the next charge had to push against that potential. We had to do an integral, which is why you got this half floating around in here. And then the only thing last time I did a little weird is we often like to write the energy in terms of the charge, if you know the charge, but also in terms of the potential difference, if you know the potential difference. And I just was dumb and I substituted here, and that's not what I meant to do. I meant to substitute here. All right. So if we want to substitute here, what are we going to say? We're going to say Q is CV, C delta V. So you square that, C squared delta V squared here. One of the C's goes away, and you get 1/2 C delta V squared. So those are your two energy of the capacitor equations. They're the same thing. You're just using different versions of this. You could write one in terms of Q and V if you wanted to. I think it's 1/2 QV squared, I forget. Can you please make the homework due Sunday? Yes. What a well-written request. The E field stores the energy, or the capacitor stores energy. Ooh, does the boy make the baby or does the woman make the baby? Kind of the same thing. Hard to say. One creates a condition to make an E field. What is the Q in the energy equation? The negative or positive side of the capacitor? Yes, it is just the magnitude. So remember, we'll often talk about a capacitor has charge Q. It means it has plus Q on one side, minus Q on the other side. All these equations just mean that magnitude Q. You would never say, oh, I have to double it. It's always just the amount of charge separated one on one, one on the other. So never double it. So when I write Q in these equations, it just means the magnitude of the charge on each one. All right? That was a quick review, but we actually have one more concept that we have to stick in here. The final concept for capacitors, because the trick with capacitors is you want to get, you want to get the capacitance as high as possible. You know what I mean? You want to get the capacitance high. So there's one more trick. Like right now, you can imagine how are you going to get the capacitance to be really large if you're designing a capacitor? You're going to change the permittivity of the universe. No, you're not going to do that. You're going to make the areas as big as you can, and you're going to make the separation as small as you can. So if I was trying to maximize this capacitor, this 1912 capacitor here, I can't really change the area of the plates, but I can change D, and I can get it down to sub-millimeter, but then they're not perfectly parallel and they touch. Right? So high capacitance, low capacitance. Okay? So let's think of one more way we could increase the capacitance. And it's a very physical idea. That's why we like to talk about it. Is we think about putting a dielectric inside the capacitor. Dielectric means insulator. Dia means through, so the field goes through it. But first, before we put it in a capacitor, let's put it in an E field. So many E's. Let's think. We're going to have a big electric field like this in space. We call this a uniform field. As you know, we're going to call that E naught. Okay? Big uniform field. Everywhere you go. Points that way. We're going to put a material. Well, I'm already winded. What time is it? Lord. We're going to put a material in this uniform field like this. And this is going to be a dielectric, an insulator. Not a conductor. And when we had a metal, we said the free charges in the metal, what do they do? Well, they're electrons. Free charges are electrons, and they move this way. So we said there's some negative charge over here, leaves positive charge over here. Right? And we said that happens until the field inside is 0. Well, that's not what happens in a dielectric. In a dielectric, you do end up with some charge on this side, negative, and some charge on that side, positive, but it's due to the little neutral atoms getting sort of warped. You know, the atom was neutral, but when you apply the field, we drew this before, I think, you get a little bit of the negative charge of the atom over here and the positive charge of the atom over there. So you polarize the individual atoms, and this is how we talked about polarizing a material. I think, yeah, we talked about this before. Right, so the field just shoves the positive. Oh, I'm sorry. I drew it backwards again. Damn it. Which one should I flip? Negative. Oh, I'm about to do it again. Negative, positive. So you got to think a little. What kind of charge is going to flow this way? A negative charge is going to run away from the field, the positive charge that created this field. No, I had it right. God, what's going on? I think I'm about to pass out. Let's see. A positive charge will move down the field, right? Yes, I had it right the first. Does somebody want to come take over? I'm really just an actor. I don't actually know what I'm talking about. I just draw these on the board and rant, and then I get good reviews. I don't know how it works. Okay, so. Okay, I was right in the first place. Just delete that last minute. We'll fix it in post. So what happens then is this is basically like a positive charge here and a negative charge there. Right? So this creates its own field. E induced, I-N-D. So E induced created inside the material due to the charge. Right? Just like in the metal. We said there was an E induced, and in the metal, the charges will keep moving until the field is 0, and in the insulator, that just doesn't happen. They don't move that far. What is the upper E on the right side of the board? Oh, I don't know. E, that's just the electric field in the gap. I'm not going to put a vector sign on it because I just gave you the magnitude. It's the electric field in the gap. Okay. Okay, so what happens is the polarization lowers the field inside the material. But it does not take it to 0, like a metal. Not to 0. And it's just because the charges aren't as free to move. You know, the charges are limited. They can move, they can shift the atom a little bit, but they can't move all the way across. Okay? So what then we would say is the real E inside the material, the actual field inside the material, is just the superposition. The external field plus the induced field. Right? And you say, that looks like it's going to increase it, but they're in opposite directions. Right? These are not in the same direction. Right? So opposite directions, and they're adding like vectors, so that's why E inside is reduced. So let's look. Quick question. So in a conductor, the whole thing is polarized, but in an insulator, individually polarized molecules, sort of in a conductor, there's electrons that are free to go all the way across. So you just can get a bigger effect. And there's so many free electrons that you could cancel almost any field. Now in theory, in principle, you would reach the limit of this. If you apply a big enough field to a metal, you will field evaporate it. Right? Atoms will just get ripped off. It's like sublimation in a physics lab. Okay? You can sublimate materials with fields. More likely, the air would break down first and you would get a discharge. Why does E induced move from... it's timed out. Move from negative to positive, but normal field's positive to negative. Yeah, good question. Okay. What created this uniform field? How do you create a uniform field? There must have been a giant plate out here at the edge of the universe creating it like this. Therefore, the external field did go from positive to plus to minus, just like I eventually drew over there. But remember that the material will get polarized the other way. The material will put the positive charges over here, the negative charges over there. So E induced is just due to the material's charges. Okay? So E induced created inside the material by, I don't know what to call them. The material's charges. That's too long to write. You write that down. By the material's own charges. And those are going the opposite way. That's why. Okay? So what you do then, mathematically then, there's like 5 parameters you can define with k plus 1, all this stuff. So we're just going to talk about the important one. So the way we handle this is we define something called, I believe it's kappa, but I can't write a kappa. So I'm going to write a big K. That's like a problem I have. Is you say that kappa, the dielectric constant, is the field you apply divided by the E inside. So is the dielectric constant bigger than 1 or smaller than 1? It's bigger than 1. And the more a material does this, the greater extent that it cancels the field, the higher kappa. All right? So let's look at a few kappas, or K dielectric constants. Here, I thought I had a few written down. Having all kinds of problems today. Oh, I deleted all of them. I can tell you the ones I know. Here we go. So K equals, you need the word, I guess, dielectric constant. All right, so K of vacuum equals, do we all know this one? This high-level theory we've been doing, can you predict K of a vacuum? It's either 0 or 1. You got a 50% chance at it. It's 1, correct. There's nothing to get polarized, right? So the E induced, there's nothing that's going to be 0. So you make that 0, E equals E naught is 1, right? The vacuum just is 1. K of air, 1.0006. There's one more 0 in there. Okay, it's really close to 1 is what I'm trying to say. Just like the refractive index of air is basically the same similar phenomenon at high frequencies, it's really close to 1. K of Teflon. So like a typical plastic. I think it's 2.4. Not sure. And then K of water is 80. Why is water have such a high dielectric constant? Because it has a large dipole moment, as we've talked about. And Hannah tells me y'all didn't like the water problem? It was so pretty and fun. Like, no, I can see people shaking their head. I don't know. I thought it was awesome. So you've got a dipole moment like that, and the water molecules are free to spin around. A solid material like Teflon might have some nice dipole moments, but they're rigidly fixed. But water, big dipole moment, it can spin around and align to cancel the field, so water has a large dipole moment. Or water also has a large dielectric constant. What is the difference between E induced and E inside? So E induced is the electric field created just by these charges. Right? That's the induced electric field. E inside is just the loosey-goosey term I'm saying that if you add up the two fields in the region, the applied field and the induced field, you get some, that's the actual field inside the material. If I were a little test charge and I went in here, I would accelerate according to E inside. It's the actual field if you measured it. But it's due to these two effects, E naught being applied by the big plates, E induced being applied essentially by the surfaces of the material. If we go too much further, we're doing vector calculus, so we have to be very careful. We don't want to do that. Will these K values be given in a table on the test? No. I don't know. We haven't thought about the test yet. We're still finishing the last test. We haven't made this test. If you've been in this class all year, you could probably imagine that I'm not going to make you memorize a table of dielectric constants. How many things have I made you memorize? Your name. That's the only thing you've had to memorize for this class. So no, you don't have to memorize dielectric constants. Okay. Some of you even forgot your name on the exam, and we didn't even count wrong for that. So you literally have to know nothing to get through this class. Absolutely zero. Okay, so the reason we talked about the dielectric is we're going to put it in a capacitor. We could drive all the equations, or I could just do it. Are you ready? Okay, next topic. Okay, dielectric in a capacitor. Let's see what it does. And here is where you get a little bit of insight about fields and how they behave, and it's actually a little bit counterintuitive, so it's a good chance to really think about what's going on. So let's draw the dielectric without the capacitor without the dielectric real quick. I won't keep drawing the battery. Well, I probably should. So here's the positive plate over here. Drawing this a bunch of times is good for you. Yeah, there's delta V, some battery creating a delta V. You know, that's the battery, say. So it's going to create an electric field. Let me see if I can get the direction right. I'm a little test charge short and stout. It's this way. That's how I get it. I sing that every time, okay? There's the electric field. And then we have D is a separation. Typical capacitor problem. If we gave you this number and this number, you could calculate E. And then you could calculate the charge. Let's see. So what's going to happen if we put the dielectric material inside? Same capacitor. We're going to go ahead and we're going to hold it. I didn't write down if we're doing the same charge. Let's see. No, okay. Let's not worry about it yet. I forgot what point I was trying to make. Got the same amount of charge on the plates. Okay? And we're going to put the dielectric in here, and it's really going to touch, but I'm not going to draw it touching quite, just so that you can see the boundaries. So we put a dielectric in there, K. It's going into a field. I'll write it as E naught. The original field was E naught. Put in a dielectric K. What happens? It gets polarized. It makes charges opposite to what's creating the field. So, of course, it gets polarized. The positives go here, and the negatives end up on this side. Okay? And what do we know happens is that the E field inside is reduced. It's exactly what we just talked about over here. It's just I'm showing you the plates up close, or I'm calling it a capacitor. Okay? The D didn't change. It's still a D. But what could happen is the field changed, the amount of charge could change, and the potential could change. All those might be changing. The only thing we know isn't changing. D is the same. The area is the same. That's all we know is the same. All right? So the way to figure it out is we say, okay, what do we know? We know that always that the capacitance is Q over delta V. Right? That's the charge over the potential difference. That's just the definition. I just rearranged it a little bit. The charge you get is the capacitance times the potential difference across it. And remember, you always have the case that the relationship between the potential difference and the field is just the field times D is delta V. Okay? So we could also write this as is always true. Q is E, or so the capacitance is Q E times D. Okay? Because delta V is E times D. Right? Those things are just generally true. You just got to figure out which field are you talking about and which delta V are you talking about. Okay? So the way I was going to write this out is to say, okay, we started out with the capacitance equal to Q over delta V, right? And then we said, okay, that's equal to Q. And instead of calling this ED, we're going to say when you put the stuff in, it's E naught over K times D. Right? So we've lowered the electric field, right? I guess what I was trying to say here, this is like the original capacitance. Here we go. So the original capacitance was E naught, the original amount of charge, the original electric field, same D. Right? So we're saying what is the new capacitance? Right? And then what you would do is say, well, this looks just the same. Yeah, we took, I'm sorry, this is what I need to take this off. Okay. We just had some charge on it. And now we put this thing in. That's what we're doing. So the charge can't go anywhere. It's the same charge. Right? So all we've really done is taken the field and reduced the field by k. Okay? That's all I've really said. I'm sorry, I went in a bunch of circles here. This is the same. Yeah. Okay, sorry about that. We're doing this whole problem in terms of charge, or this whole argument is in terms of charge and field, not really delta V. So originally we had the original capacitance was the original charge over the original field times d, and now the new capacitance is the original charge, can't go anywhere, over E naught over k times d. So you can see the k just goes in front of the original capacitance. Okay, so that was horrible. Go read the chapter on that. I don't want to do it again because I've wasted too much time now. But basically, when you put in a dielectric, the capacitance goes up by a factor of the dielectric. Okay? So if I have this capacitor set up like this, here we go, like that, and we were to calculate it, we'd get probably like 100 picofarads or so. And then I take this wood, the dielectric constant of wood depends on the tree, but it's like 2, okay? So I put it in here. Now the capacitance is twice what it was, right? Here it's 10 picofarads. Now it's 20 picofarads, okay? So sorry that derivation didn't make any sense, but the result is very simple. You put in a dielectric, and it multiplies the capacitance by the dielectric. And sort of the physical reason I can maybe recover, the physical reason is the amount of charge effectively at the surface went down. Okay, so the potential you needed to make that charge was less, right? So you'd have to have a lot more potential to get the same effective amount of charge. You've got to overcome this charge here is the physical reason that the capacitance value gets affected. And it's still just geometry. It doesn't depend on charge or potential. It's still just the properties of the capacitor that's setting the value. It now is filled with a different K than 1. Now it's 2. Okay? This is how capacitors are made. So if you've seen capacitors before, they're like this big. And we calculated for 2/4 of roughly this geometry was picofarads. But some capacitors are up to microfarads or millifarads. So how do they fit 1,000,000 times more capacitance in this than just a couple of plates together? And it's like this. If you take this apart, and I used to do it live, but it would take a while. If you take this apart, it looks like this. Ooh, all this stuff. And the can comes open. Oh, I couldn't get that one apart. Oh, I couldn't get that one apart. It's like a can holding these electrodes. So these are the electrodes, these gray things. And between them is some paper, and it's wound up like this. So the only space between these two is this thin paper, right? So that gets the gap really small. D, epsilon naught A over D, that gets D really small. And then we put in water. So that gets you 80 times more. And the only reason the paper is there is to keep them from touching. The paper sets the D. And then you put in salt water. So if you have an ionic solution, electrolyte, the charges can move to the paper and move around in the paper. And this goes even higher, hundreds. And that's how you can get a huge capacitance in terms of inside of a teeny thing. Guess what these do sometimes? They explode. So in the 80s, when you had a computer, I had a computer in the 80s, Apple IIe. Okay, every now and then you're playing, D&D on your Apple IIe, and you're kicking ass, and it's really awesome, and you hear pop, and smoke comes out of your computer because one of the big capacitors in the computer exploded inside the computer. It happened like once a year. For me, about once every 2 months because I was on the computer sort of 24 hours a day. But that's actually where the phrase "pop a cap" came from. I'm going to pop a cap in your ass. That has nothing to do with a gun. It's actually a capacitor thing. At least in the 80s, that's what pop a cap meant. I'd take my thing to the computer store. Oh, I popped another cap. And they're like, oh, okay. You should move. I don't know. And now we're done with capacitors. So the current homework 7, not the one due now Sunday, we'll have some more capacitor problems on it, but it'll also have problems about what we're about to talk about, current resistance. Okay, so for current resistance, here we go. So now we're switching to chapter 27, I think. I'm just going to set up a question for you and let you stew over it during the break and decide what's going to happen. We're going to set up a paradox in the universe and see what God does to us. We will include God in the discussion for this one demo. Okay, here we go. So say I have a conductor. Okay, so here is a conductor, and I have a battery down here. Plus. Oh, shoot. No, yeah, that is plus. That's minus. Okay? So according to the laws of physics, are going to go up against the laws of chemistry. Who's going to win? Okay, so what we're going to do is we're going to take a conductor, a wire, and we're going to touch it across this conductor. Okay? So what does physics say? Physics says delta V on the conductor equals 0. Physics says you can't do that. Right? Because then you would be saying this has to be at plus 9 volts and this has to be at 0 volts. And that can't happen. We said that the field inside has to be 0 and that therefore the potential across the surface has to be constant. That is impossible. What does chemistry say? Chemistry says delta V must be 9 volts. It says you have to have a 9 volt difference because it's an electrochemical battery and there's an electrochemical reaction happening. So who's going to win? Oh, I don't know. We have to wait 5 minutes to find out who's going to win. It's very exciting. Who has protective eyewear? Okay, 5 minutes. Go get your protective eyewear. No, yeah, you'll be okay. I covered up the answer. I covered up the board, but you remember what it said. What's going to happen if we put a conductor over a battery, terminals? We're going to break the laws of chemistry. We're going to break the laws of physics. 1, 2, 3, say chemistry or physics. 1, 2, 3. Oh, half and half. Let's find out. Let's see. So this is a pretty fine wire. And I'm just going to touch it over the two terminals. You probably can't see the wire yet. Oh, physics is winning. I can't. There's a magic force field. I can only touch it. No, here we go. Here we go. Wow. Did you see that? It just broke. Whoa. Ah, it's going to burn me. So it bursts into flames and disappears. So that's why the universe says you can't do that. It can't exist. So in physics, if you do something that can't exist, it bursts into flames and disappears. That's what we're learning. Look at that. All right, who won then? Chemistry won. Damn it. I hate it when chemistry wins. It's so rare. I guess they have to have something. So rare. So what happened? Let's see what happened. What happened is we have to remember our law of physics. Which law did we break? We said we broke this law, but we forgot one teeny qualifier. Anybody really thinking, read ahead, seen this before, would know the qualifier is delta V on a conductor is 0 in electrostatics. We're not electrostatic anymore. Right? We're going to let current flow. We're going to let the charges move. When you put a conductor in an electric field, field inside is 0. The potential on the surface is constant, but not immediately. It takes it some time to get there. Right? The charges have to move to make the field 0. So the first instant, it's not 0. The charges have to get there. So what we've done here is we've said, okay, some electrons will, well, let's pretend they're positive. Let's say some positive particles flow out of here, but then they see a path to here. So you put up more, and then they see a path here. So the charges are trying to drive the field to 0 in the metal, but they can't because as soon as one comes out, one goes back in. And they just go in a circle, and they go in a circle. So we have moving charge, which we're going to talk about how that heats up the material and catches it on fire, etc. All right? So these kind of batteries you don't see as much anymore. They're very dangerous, okay? Both electrodes are right next to each other on one side, and it can put out several amps of current or enough to catch things on fire. So do not put these in your pocket. Never put these in your pocket, okay? Because if they touch your keys, they'll generate a spark much bigger than that in your pocket. So don't do that. If you're ever lost in the wilderness, you do want one of these. Because if you have this and some steel wool, and you touch this to the steel wool, it bursts into flames in your hands, and you can start a fire, hopefully like with some kindling and not with your hands. So anyway. Which I usually do, but I couldn't find my damn steel wool. I'll bring steel wool next week. I don't know. Okay, so that's what we're talking about. We're talking about current and the motion of charge now. So we're not doing electrostatics anymore. We're not really doing electromagnetics either, but we're doing something in between called electricity. So current is the word. This is what the next chapter is all about, current and resistance. It is the flow of charge. I was told I could be on the lacrosse team because I have good flow. I have no idea what that means. Okay? I don't want to know what it means, but that's my new version of the word flow. So it's the flow of charge, usually electrons. Usually electrons in a conductor. Okay? Usually electrons in a conductor, but also, it doesn't just have to be that, more relevant possibly to you, if you're doing chemistry or biology, ions in solution. Or, if you're going to do plasma physics, charged particles in space. Or think about the sun, or aurora borealis, charged particles in space. So that's pretty much the main three currents that get thought about in the world. Either electrical current in a metal, ions flowing, which is how your whole body works, or plasmas in space. So we wanted to draw it. We're mostly going to talk about electrons in a metal. Okay, so here we go. Here is a cylindrical conductor. But we are going to pay for the sins of Benjamin Franklin. All right, so Benjamin Franklin originally, so this is maybe apocryphal, but let's just say, Benjamin Franklin originally set the idea that certain things were positive and certain were negative, and then once they figured out how the atom works, the electron came out negative. Damn it. It would be nice if the main thing that flows in a metal were a positive charge carrier. And then you could say the current, I, is flowing that way, and the electrons are flowing that way. That's actually not the case. The electrons are flowing the other way. So the current goes one way, the electrons go this way. So what we do is we take the blue pill and we just say the charge carriers in a metal are positive particles, even though they're not. Okay, we just pretend. You can think of it as though there are positive charge carriers, but really it's electrons flowing this way, right? Electrons flowing this way. One way to make us feel better is we say it's a hole. A hole is a place where there is no electron. So if all the electrons are flowing this way, this hole is flowing that way. Okay, so if you want to refer to holes, you'll sound very advanced. So I don't know. You got to think about it how you want to think about it. If positive particles are flowing this way, which end do you think is at a higher potential? Let's see, positive going that way, like charges repel. So this side of the wire is positive, and this side of the wire is negative. And that's why if this current were the flow of positive particles, the current would be going that way. But you know, in reality, the electrons are attracted to the positive side, and the electrons go this way. I didn't create all this, okay? Is that Philander or Benjamin Franklin? So if we look at it, then the mathematical definition of current is that it's a flux. It's the change of charge, the flow, the amount of charge that crosses some area. Okay? So this is, I'll just say in coulombs per second, or amps for ampere. And amps are the abbreviation is A. So you've probably seen that in your life. MA for milliamps, micro A for amps. Probably seen that before. Okay, so current is a flux across a surface. That's one thing to remember. Current is flux across a surface. Flux is one of those old-fashioned words that physicists just can't let go of. Okay, we still like to say flux. It really just means the number per second per unit area, or across a surface. In this case, we're not doing per unit area. In this case, it's just the number of charges across a surface per unit time. That's all it is. So we just simply count all the little positive charges that go across a cross-section per unit time, and that's the current. Okay. The direction is it goes from positive charge from high to low. From high potential to low potential. Okay? So you can just memorize current I goes from high potential to low potential, or you can think of current I as a positive charge moving. How would a positive charge move? From high potential to low potential. It will give up its potential energy to gain kinetic energy so it can start moving, if you want to think of it that literally. Okay? And then, like I said before, all equations basically pretend that it's positive charge. I is defined as positive charge. In reality, you might have a system where it's negative charge, like all metals. Okay? In an electrochemical system, you may have both happening. You may have some positive charges going this way and some negative charges going that way, and then you actually add them up. There's a case where they're not canceling. The positive charge going that way represents current that way. The negative charge going this way also represents current going that way. So if it's got both going, you actually have to add them together. Okay? They would only cancel current if they were both moving at the same way, which wouldn't make any sense. Right? They're going to move opposite directions. It's just in a metal, you don't get the advantage of the positive charge moving in addition to the negative charge, because in a metal, only the negative charges move. Okay? So usually what we do from here is we say, okay, so I is the current, and then I'll go ahead and just for fun, we kind of need it a little bit, is define J as the current per unit area. There's also the current density. And it's nothing mysterious or complicated. It's just sometimes more convenient to talk about the current I divided by that cross-sectional area A. Right? So J is I over A. I is delta Q, delta T over some area. So all you're doing is dividing by that area to get J. So current or current density. Okay? So it's like a surface density, not a volume density. Right? So to get a good microscopic view of this, we want to think about how are the charges really moving? Like what's really going on here? So let's look at a microscopic view of current of it here. So you'd draw sort of the same diagram again. You'd say, okay, I got a cylinder. Let's do a conductor, and say there's a bunch of little, let's pretend they're positive. They're not. Let's say there's current flowing that way, a bunch of little positive charges, and they're moving this way at something we call the drift velocity, V drift. Okay? They're just kind of flowing. We'll get into exactly why and how they move in a minute. But for now, just say they're drifting. And then you got to have, if you're going to define current, you got to think about some cross-sectional area, right here. And we're thinking about how many cross that area per unit time. Okay, so how many cross A, so A can mean the area, and I'm just labeling that surface per unit time. Let's just say in delta T, be a more direct way to ask it. Okay, so they're going V drift, so the ones that are right at the front are going to end up how far away? They're going to end up here. All right, they're going to go a distance delta X. So all the ones that are here, all the ones that are right at this interface will move forward. And how many will be in this volume is how many crossed. All right, so how many cross in delta A is the, let's see, how many cross A in delta T is the question. The answer is the number in this volume here. Can you see that? It's just particles flowing along, and the number that cross for delta T is just say how far do they go. So we just got to use D equals VT. Right? They're going V drift. How far do they go? That delta X is V drift times delta T. So there's nothing specific about this being charged particles. This could be water molecules. This is just general flow. If you want to think how many cross a plane, it's how big is the pipe and how far, or not how big is the pipe, it's just how fast are they going down the pipe, and how many are there? Okay, so we want to put that all together. That's not what I meant, right? Okay. Okay, it's the number in this volume. So we got to know is how many are in that volume. So we're going to take delta Q over delta T. So we want to get the area. So we're just setting things up here. Okay. This volume will clearly be this area times that delta X. We're going to know how many are in there. That many cross in delta T. Okay. How many cross A in delta T? The number in this volume, right? Okay. But we need to turn it into a charge. Okay. So now let's turn this into a charge. It's NQ, I'll tell you what these are in a minute, times Q times that volume, which is A times delta X over delta T. Okay? Let's see what that means. A delta X is the volume. right? That's the volume of this little cylinder that they moved into. NQ is the number density of the charges. It's like there's 10 billion per cubic meter, right? Just the number density. So it's like the number per meter cubed if we wanted to do it in MKS units. And that's something you just be given. Like in a metal, there's a table in the book, you don't have to memorize it, of the number of free electrons per meter cubed. And it's really big. It's like 10 to the 22. And it's different for different metals, which is part of the reason different metals are good or bad conductors. And then what is Q? Is the charge on each carrier. Right? So you take how many of them there are times their charge, and that's the total amount of charge, times this volume per unit time. Right? So you can see that this volume times this cancel the units out. Right? The number per unit volume times the volume, the total number times the charge, the total charge per unit time. Right? That's what it flows by. So one thing then we can do is substitute for the delta x and make it v drift delta t. And that'll make the delta t go away, basically. NQ, so the number density of charge carriers, the charge on each carrier, the cross-sectional area, the v drift, how fast they're going, delta t over delta t, right? And the delta t's to go away. So this is all the current. Equals all that. So this, let me just write the final one, and then we'll just think about it for a minute. The derivation isn't that important. It's really just what does it look like. You get that the current, if we have charges flowing, current equals the charge on each carrier, the density of each carrier, the cross-sectional area, and how fast they're moving. And in terms of a microscopic picture, that would make sense. Right? So we're not talking about the potential causing them to flow. We're not talking about the electric field. We're just saying a bunch of particles are moving. Right? Well, I would expect that the current would be bigger if the particles had a lot more charge. I would expect that the current would be bigger if there's a lot more of them moving. I would expect it to be bigger if the area is bigger. Because remember, I'm only telling you the number per unit volume. So the area is bigger, there's more of them. And I would expect it to be bigger if they're moving faster. So if you're only given these kind of parameters, there's your current. Right? And you can see, if you wanted J, you would just get rid of this A. The current density is just independent of the area. It's the current per unit area. So it'd just be the charge times the density times how fast they're going. So what the point of this is trying to stress is these are the important parameters. What's the charge of your charge carrier? How many of them are there? And how fast do they move? That tells you what current is. Okay. Okay. So now, but what we care about is what makes them move? How do they move in a circuit? It's really, I'm talking about putting this thing on a battery and having the battery makes it move. Having the battery make it move. So let's think about how that works then. Let's see. It is by something called Ohm's Law. Okay? May I go off for a second? Yeah, so Ohm's Law is not a law. Okay, so the way science works is you have this bullshit in your head that you're told in middle school that we have a theory and then we test it. Or no, we have a hypothesis and we test it, and a theory and we test it, and it becomes, everybody believes it becomes a law. So if it's called a theory, it's something we haven't figured out, we're not sure yet. If it's a law, definitely true. Almost the exact opposite ends up being true. Okay? We still call it the theory of special relativity. That's a law. We call it Darwin's theory of evolution. That's a law. A lot of things we call a law aren't even a theory anymore. Okay? This is not a law. This is not a law. This is Ohm's observation that is somewhat accurate and relevant to materials of interest in 1827. Okay? That's all it really is. So do not think of this as a law. Okay? The way you write this law, the famous way to write it, is that the voltage you put across an object equals IR. So what this law is really saying is that the more voltage you apply, the more current you get, and that it will be linear, and that the constant of proportionality between them is what we call the resistance. Okay, so R equals resistance. I'm sort of defining all these things before we derive how they work. We're going to try doing it that way. Resistance, and that is actually a constant of material in geometry, a constant of the material's properties, but also the geometry. We'll get a formula for it later. Okay, so that's actually an extrinsic property. If you have a wire, it has a certain resistance. If you have twice as long of a wire, it has twice as much resistance. It's not an intrinsic property. You'll also see Ohm's Law written in essentially the same form. If you, instead of thinking in terms of delta V, you think in terms of the field, right? That's delta V times L. Is E over L. So you turn this into E, and you make this an intrinsic property. And you say the current density equals sigma times E. This is what he really said. Okay? So this is useful when you're doing calculations on circuits. This is useful when you're doing other things, thinking about plasmas in space or trying to derive what the resistance is. But these are the same thing. Okay? In this case, this is the conductivity. Okay? So it's sort of like the opposite, the inverse of the resistance, but it's also intrinsic to the material. There's no geometry involved. Intrinsic to the material. All right. It became intrinsic because we switched from delta V to E, so that kind of takes the length aspect out of it out, and we went from I to J, so that takes the area aspect out, and that's why you would write that one as sort of an intrinsic property. But the whole time, what we're talking about is we have a cylinder on a battery, plus, minus, and we cook one up here, and we get an I, and we have a delta V of the battery. So we're just trying to figure out, if you apply delta V, how much current do you get? There it is. That constant tells you. Or, if you want to be fancy pants, you say, well, I want to divide my I by this cross-sectional area and call it J. And instead of thinking about the voltage, I want to take the voltage times this length to get an E. And I want to invert that and call it conductivity. But it's the same thing. Okay? So most materials in 1827 were ohmic. So Mr. Ohm set something up, and he put his delta V here and his I there, and he plotted it like that. And he got a line. Measured the slope of the line, said, that's my resistance, turned it into Dr. Dodd's. And Dr. Dodd said, the resistance is the inverse of that slope. Oh, you got it backwards, right? V equals IR. So R equals 1 over the slope if you plot it that way, which is how we usually plot it. Okay? Materials can also be non-ohmic. In fact, any material, if you measure it close enough, it's not really ohmic. It really do something like that. Or it might do something like that, or it might be a superconductor. Nothing is really perfectly ohmic. So that's why it's not really a law. It's more of an approximation that's really accurate for metals. Can you explain the volume again? J what times E? So yeah, so what? So this is a sigma, and it is the conductivity. It is not the charge density. Right? So on a parallel plate, that was a charge per unit area. Now it is the conductivity, a property of the material. We changed chapters, so I get to reuse the variables. I'm just doing what your book does. Can you explain the volume again? I think that was from way back there. It's too late. You'll get there. This is all laid out very carefully in the book. I'm going a little fast. Okay. What are we going to get through here? We're not stopping. We're just thinking. Let's now look at the, what is the slope again? Can you explain the graph? The graph is simply, let me draw the graph real big. I'm in lab. Here I am in a lab. I've been given this piece of material, and I've been given a little voltage source where I can change delta V, and I put a wire here, and I put a wire here, and I measure the current. So I take my data. I'm going to do it at 1 volt, 2 volts, 3 volts, 4 volts, and I'm going to measure the current. I. This is the delta V I'm applying. I'm going to say at 0, I get 0, hopefully. Better null the detector if I don't. 1 volt, I go up. Oh, I measured that. Put it at 2 volts. More voltage, more current flows. Right? It's bigger. Measure it again. 3 volts, it goes up again. 4 volts, it goes up again. And I fit a line to it. And it's an intro physics lab, so I measure the slope. I mean, what else do you do? Right? And I say, what is the slope? The slope is 1 over r. That's all that was. I was describing a lab exercise. So that's usually how you measure the resistance of something. All right? It won't really be a line. Then you can call up Ohm's descendants and yell at them if you want. Okay. Apply constant. Yeah. So here's the mystery. So the last thing we'll do is we'll solve a mystery. And let's see how much of them I'm leaving for next week. Oh, not too bad. Let's have a little mystery party here. Let's think about what's really happening inside this conductor. Yes, what's happening inside? Let's think about what we're really doing here. We really have this battery, a positive terminal and a negative terminal. And we really have this metal like this, right? And I take a wire and I stick it to the positive side here. And I take the wire from the negative side and stick it here. So this is at kind of the high potential, and this is at kind of the low potential. And that's the reason the current flows, is that forces there to be an electric field inside. And normally in a conductor, the charges would move to make that field 0, but now they can't. Right? This electron sees that and says, I've got to move over here to make it 0 because that's what I'm supposed to do. So the electron is here, and it moves to here, and it moves to here. I did it. Oh, shit. Oh, I fell in the battery. Right? That's why it doesn't. That's why you get a current. Is the charge can't just move and sit on the plate. It goes into the battery. Okay? All right. Plus, we could imagine positive charges feel a force this way. Right? So does anybody see the kinematics disconnect we have here? What are those charges going to do if they feel a force? What kinematic thing are they going to do? They're going to accelerate, aren't they? But what did I write here? Nowhere. Oh. Oh, there it is. What did I write right there? No, right here. What is this? Drift velocity. And I sort of implied that it's constant, didn't I? Yes, I did. Okay? So it would seem that the electrons are accelerating here in our simple picture of things, yet we imply that everything was just moving along at a constant velocity. So we've got to figure out what's really going on. I can show you in one quick video while I erase boards. Here we go. The perfect explanation of what's going on. Get ready. It may be the greatest physics explanation in the history of physics. Is it on? Do screen controls unmuted? Yes, that is what's happening. Yes, watch the balls fall through the pachinko machine. So are the balls experiencing a gravitational force? Yes. Are they accelerating down? Yes. But look how they're moving. They look like they're moving with a constant drift velocity, don't they? See how they're just kind of slowly going down at the same kind of, see, constant drift velocity. But they should be accelerating. So they're not accelerating because they're banging into the little, whatever those things are called, the little pins. Okay? So the same thing is true of electrons going through a metal. They don't, when they drift through the metal, they don't really smoothly drift. They're banging around off all the atoms. Okay? And they're slowly making their way. So in between banging into the atoms, okay, not really the atoms, just don't tell anybody I said that. In between banging into the, oh shit, let's turn this off. I don't know what's next. Who knows? Pachinko casino video, what's next? Who knows? Another way you could think of it is that the electrons are at their terminal velocity. Okay, so like when a skydiver jumps out of an airplane, who here has skydived out of an airplane? Surely someone has. No one here has done the tandem? Wow, okay, I assume one of you had. Okay, I haven't, I'm not crazy. Okay, right? So if I take this thing, this is like a skydiver, and it's going to feel a gravitational force, so it should accelerate down, but it doesn't. It just goes down at a constant velocity, right? Because it's at terminal velocity. So the charge carriers in a metal, while current is flowing, are at terminal velocity because of all the resistive forces that they're experiencing in the metal. Okay? Let's see. So let's describe that real quick with a few equations here. Oh, no, we don't do it that way. we could just skip all that because there's really no equation to go with it. It's really just 2 pages of why that happens. Okay, so screw that. Okay, so let's look then at that. So those resistive forces are y. You have just a constant drift velocity, and yr is just a constant. There's no acceleration involved. So an object just has a constant r. Okay, so let's do this last thing. Let's just talk about how to calculate the resistance, because you definitely want to know that. So resistance depends, like I said before, on material properties and geometry. Okay? So first, let's look at it. And the resistance of a cylinder is really what you use for pretty much everything. We're not going to drive it. We're just going to write it down. So if I have a cylinder like that, it's got cross-sectional area A, and it's got length L. Because you can imagine those are going to affect the resistance. The longer it is, the bigger the resistance, and we'll see. And it also has a property rho. Okay? So rho is the resistivity of the material. And that is an intrinsic property. Doesn't matter how much of the material there is, it's always the same. It's a basic property. And before, when I wrote Ohm's Law for you, I wrote it in terms of sigma. Well, it's just 1 over sigma. Right? Sigma was the conductivity. You just flip it over, you get the resistivity. So they're really the same thing. We just like to jump back and forth because we like to be annoying. Okay? So let's look at rho of a few materials. Rho of copper. The resistivity of copper. Cu stands for copper. If you did AP out of Gen Chem, then you don't know that. So rho of Cu. 1.7 times 10 to the minus 8. Ohm meters. Why is it ohm meters? If it's a intrinsic property, shouldn't it be ohm per meter cubed? No, it's ohm meters. I won't get into why. So copper's a really good, has a really low resistivity. Rho of something called nichrome is about 100 times worse, 1.5 times 10 to the minus 6 ohm meters. Just to give you an idea of the numbers we're talking about here. Nichrome has a really high resistance for a metal and it doesn't oxidize. That's why we use it for things like heaters, things that we want to get really hot, like this. This is what heaters looked like when I grew up. That's how I set my bedroom on fire once. I was playing with one of those so I could see under my bed. Okay, rho of seawater is about 0.2 ohm meters. So you can see the difference in resistance between materials. It's orders of magnitude, right? 8 orders of magnitude between a metal and water. And then rho of glass. Anybody want to guess? 2 times 10 to the... Somebody shout out a number. 8, not even close. 14. Thank you for shouting out a small number. Ohm meters. Right? So the resistivity of glass extremely high. So there's a 22 orders of magnitude difference between metal and glass. Huge difference between resistance in materials. So then the formula that you need to calculate this resistance, we don't have time to drive it. We're just going to tell you. Oh, I don't have an eraser. Next time. Here it is. I mean, it's in the book. R equals rho L over A. Oh, except it's like this. So as you would expect, resistance gets bigger as rho gets bigger. It gets bigger as the thing gets longer, and it gets smaller as the area gets bigger. Deep reasons why we won't get into. Okay.